Got this annoying little pesky fly. It keeps bopping around. I'm trying to. Two of them, I just realised. Got one. At least we know the sound check's working. Alright, I think I got them both. And everything seems to be live now. Yep, everything seems to be up, so it's past, so let's get cracking, because tonight we are going to finish C memory. We'll check the name of this module. Learn memory management in C. So we're going to finish this one tonight, hopefully. It's been since last week, so let's see how much of C I can remember. Right, so last sort of chapter before we get to some looks like kind of theory based ones. Well, I think this is probably going to have some code in it, but anyway, let's just get on to it and let's see how we do. So, objects in C, no way. SNEC objects. However, SNEClang is built in C, and everything in SNEClang is an object. To be clear, not a class or object-oriented programming object, but a higher level data structure that holds some metadata about itself. For example, it will store what type of data it holds, int, float, string, etc. The size of the data it holds, the data itself, how many references to itself exist, at least later when we build our own garbage collector. Sec. That last point is critical because SNEClang is a garbage collecting language. We need to know how many references to an object exist so we can free it when it's no longer needed. Complete the missing definitions in snecobject.h. Here's a breakdown of all this file should define an enum called snecobject kind t with a single value integer. I'm not gonna lie, I cannot remember it in the slightest. Enums. I can't remember the syntax for that at all. So yeah, okay. I don't remember C very much from last week. Enum. But it's not going to be like that. Well, we'll put it like that for now. And then it says, yeah, like that. And it's got a single value integer. Snec object kind. A union called snec object data t with a single member. I don't remember unions either. Need to write C for a lot longer to remember this. Type def union, and it's got a single member, an integer named vint. So int v underscore int. A struct declaration with two members. So I think a struct goes like type def. Well, actually, I don't really know. To be honest, I'm just guessing. Let me find it again. Structs in C. Oh, so no need for that. It's going to be a member of type snack object kind T. So it's kind like that without the colon. Hold on, did that wrong. Type and then kind. All right, just see how it runs. Whoops. Okay, that looks right. And shift enter. Simple enough. Okay, so integer. Let's start simple with a simple single integer object. The difference between a snack integer and a regular C integer is that the snack integer is allocated on the heap, can store additional metadata about itself. For now, it's just its type. The virgin C integer is allowed on the stack, doesn't know when it's being used. Chad snack lang integer is allocated on the heap, knows when it's being used and abused. Assignment. Complete the new snack integer function. In snack object C, it should use malloc to allocate heap memory for a new pointer to a snack object T. Blimey, I'm going to struggle to remember all this. It is completely gone out of my head from last week. So use malloc to allocate heap memory for a new pointer to a snack object. Snack object. Set the kind field on the new snack object to the integer enum value defined in snack object. So I think it's just snack object dot kind equals enum value. Forgotten how that works. Is it like that? Integer. Enum. I think that's right. Needs a semicolon though, because C, everything needs C, semicolon. Set the vint field of the new snack object to the integer value passed in. Return the pointer to the new snack object. Return snack object. Forgotten how to use structs apparently. Structs in C. So error memory reference base type int asterisk is not a structure or a union. What's wrong with this? I'm going to rename this just to avoid new object. Just to avoid. Doesn't have to have a asterisk, does it? Don't have to point the reference out, do I? Member reference base type is not a structure or a union. Oh, hold on, it's 1 times. Whoops. Is that right? Oh god, I just forgot. I just completely forgotten like all sensibilities with C now. I just completely forgotten it. 0%. Member reference base type int star is not structure or a union. Nope. Oh gosh, it's gonna be a long night. Oh, back in a minute. Important job of the day is done. Right. I'm forgetting very basic C things here. So I think I'm going to have to speed things up a little bit. I think we're going to have to get Boots involved because I'm looking at it, I'm doing basic things, and I'm just not. Let me go back to structs just to, just to give myself a little refresher. Come on. They're pretty simple. So what did I get wrong with it? What am I doing wrong here? Just basic stuff. What's wrong with it? Member reference base type int star is not structure or union. Error type name expected expression is not a structure or a union. Is that just the case I have to return the pointer like that? Nope. What am I doing? That's right. I just forgetting something really basic. Ampersand. Nope, that's not right. Nope. All right, I'm gonna have to ask Boot. We get through this. So I'm gonna have to rely on Boots. Like it's been a while, and I've completely forgotten how C. Oops. How C works. No worries, young. C can be tricky to remember after a break. Let's work through these compilation error steps step by step. So looking at your code, I can see a few fundamentals of how you're working with pointers and structs in C. Let me ask you some questions to help you think this through. Variable type mismatch. So you're declaring new object as int star, but you're trying to use use it as a SNEC object. What type should new object actually be? What do you mean? Oh. Oh, because it's a pointer, gotta dereference it like that. Is that going to solve most of my problems? Not quite. Accessing instructor members. When you have a pointer instructor, see how do you access members? Is it with a pointer or something else? Setting enum values. When you want to set an enum, like, do you need to reference the enum type name, or can you just use the enum value directly? I thought you had to use it like that. Can I just do that? Oh. Well, it has to be like that. Accessing union members. Look at the header file. VIN is inside a union called data. How do you access it through a struct? Oh, forgotten. Forgotten unions. Uh, how about now? The compiler is telling you there's no member named vin directly on the struct snack object. Take another look at snack object h value. You notice that vin is actually inside a union called data. Oh. Oh, I'm a dum dum. Oh, dereference like that is fine. Code type in. Like that. Right, finally got it. Okay, let's get rolling. Ugh, okay. So, snacklang needs float. Wait, what are all these lessons? So, float, string, vector, array, get, set, length, and add. Okay. So, snacklang needs floats, obviously. How else will all the crypto bros write weird floating point bugs into their smart contracts? So, how do we store both floats and ints into the same type? So, how do we store both floats and ints into the same type? We're going to use the union and enum features in C to be able to do this. Just like we discussed in previous chapters, you will need to extend the existing snack object kind T and snack object data T types to be able to include both int and floats, and we will continue to add more types in the following chapters to exercise your newfound mastery of memory management. Assignment 2, you'll need to edit two files in this lesson, snackobjects.c and snackobject.h. So in snackobject.h, add a new enum value of to the snack object kind T called float. Add a new float field to the snack object data T called vFloat. Declares declare the new snack float function. Snack object, let's call it T. Whoops. Okay, I think I've done all that. Okay. So allocate memory for a pointer. So we're going to do this. Just going to copy this, to be honest. Don't switch below this line. Well, I just did because I copied stuff. Snack object. Allocate memory to a new point snack object. If allocation is held, return null. Set the kind field to return the appropriate enum float. And a float point object v float return object. All right, now we're speeding along. We'll get through this lesson lickety split. String. Now we're going to do our first object that has something additional allocated. When we allocate memory for a snack object that reserves memory for the object itself, small data types like integers and floats are stored directly in the object, so there's no need for additional memory allocation. Strings, however, are a different story. Strings in C are just arrays of characters, and because they can be any length, we need to dynamically allocate memory for the string separately from the object itself. So character asterisk, which is an array of characters. My string is hello world. In the example above, my string is appointed to a character array. The character array contains hello world and the terminator, null terminator. The extra spot at the end with the \0 is the null terminator. It's how C knows where the string ends. So in object, a snack object.h, add a new enum to the snack object called string. Add a new string character to the snack object data thing. So chart asterisk. Why is the indentation working? Anyway, called v string. V string. Declare the new snack string function. It's snack object C. I'm still going to steal that. Allocate memory for a new pointer. Snack object C. If the allocation is null, calculate the length in bytes using string length if the string is passed. So I guess int string length equals string length value. Allocate memory in a character field to equal the length of the string plus 1 for the null terminator. Let's call it string field. If string, let's go field. Yeah, can't remember if it's just like that. How do you do the free thing? Think that's right. Think that's right. Copy the data from the input value into the new string field you just allocate using string copy. Destination source. Copy the data from the input value into the new string. String copy. And then it was destination and source, wasn't it? So string underscore field value. Set the kind field to the appropriate enum. And then store the newly allocated string object. So string underscore field. Turn it apply to the snake object. See how it does? Yeah, few things wrong, thought so. Whoops, semicolon. Semicolon. There we go. Yay! Vector 3 is going to be the first Snake object that can hold a reference to another Snake object. It's a collection type, a type that holds other types. Arrays, lists, dictionaries, and sets are all examples of collection types. We won't implement all those types in this course, but they each will follow the same pattern that we're establishing here with Vector 3. So Vector 3 is similar to a Python tuple that contains exactly 3 Snake object elements. So in Snake, oh my goodness. Yeah. So in Snake object H, forward declare the Snake object T struct at the top of the file. It will need to be used in a circular dependency between Snake object T to Snake object data T Snake object vector. So for forward declaring, I completely forget about that. Declare forward declaring. I create a new struct called Snake vector T that has 3 fields. Type def struct Snake vector. It should be a snake lang object pointer. Add a new neat to thing vector 3. Add a new Snake vector T field. The struct type you just created to the Snake object data called vector 3. Let's call v underscore vector 3. Declare the new snack vector 3 function. Snack underscore object underscore t. The vector 3 field is not appointed to a vector 3. It's directly allocated inside the struct. We do this because we know the size of the vector is only 3 pointers wide in advance. Okay, in snack object C, we have a little run of that. Okay, so nothing's broken. Now let's add the thing. So if any of the inputs are null, return null. So if x is just like if x is equal to null, or y is equal to null, or z is equal to null. Allocate memory for a new pointer to snack object t, and if the allocation fails, to null. It's the same as this. Set the kind field to the appropriate enum. Set the kind field to the appropriate thing. Was it going to be vector 3, was it? Create a new vector snack vector t struct and set xyz field inputs to the field to the neat sec. It's going to be a new SNEC vector t. Vectors equals like this, and then dot x, dot x equals x, and then dot y equals y, and then dot z equals z. Yeah, I got it. Think I got it anyway. Huzzah. Oh my goodness, it just never ends. Arrays, get, set, length, add. Come on, give me a break now, guys. I want to get to the end of this. I got to get to the next chapters. Come on, give us a break. So, like, array. Let's add a dynamically sized array to SNEClang. We'll do it in two parts. First, we'll just create an empty array. In a later session, we'll make it useful. It's SNEC object h. Add a new enum value to this thing called array. Where's it gone now? Yeah, array. Okay. Create a new struct called SNEC array t. This is two fields. So type def struct SNEC array. SNEC array underscore t has two fields: size. The number of elements in size is a size t. Elements in array size underscore t. Size. Elements are pointing to an array of SNEC object pointers. So a SNEC underscore object underscore t elements. Okay. Add a new SNEC array t field, the struct type you just created, to the SNEC object data t. Okay. Called varray. V underscore array. Declare the new SNEC array function. So accept a size parameter. Allocate memory for a new pointer for a SNEC object. Allocate. Allocate memory for a new pointer to an array of SNEC objects. How much memory should you allocate? Think about it, probably the size of a pointer for each element in the array. We're not storing the actual SNEC objects in the array, just the pointers to them. If the allocation fails, free the first SNEC object. Allocation return null. Oh my goodness. You pointed to an array of snack objects. So snack object. So objects. And then think about it, probably the size of a pointer for each element in the array. Number of objects and the size of each object. Number of objects. Size T. Okay, set the kind field to the appropriate enum. Set the kind field to the appropriate enum, which is going to be, I forget. What are we on? An array. Array. Create a new snack array struct and set the size and elements fields. So size dot size equals size and dot elements equals objects. Probably something wrong in here, but we'll find out in a second. Snack array T, unknown type snack array T. DST. No, if obj Oh, I got it. Yeah. Three left. Three lessons left on this chapter, and then we're on to the final two. Almost there. Almost there. Got to push through. Got to push through. Hey, what's up, people? Can see a couple of you watching. Hope you're having fun. This is the final slog through this this module. Got 3 chapters left. We're almost at the end of this one. We've got 2 more after that. Okay, so getting set. We can make empty arrays, which is pretty useless, but at least the bones are there. Let's make them useful by allowing us to store and retrieve values from the array. So snack array set sets a value at specific index in the array. This is effectively array 3 equals that in Python. Snack array gets a specific a value a specific index array in the array. This is effectively print blah 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 in Python. So complete the snack array set function if the object is or the new value a null, return false. So if return false. So if the new object or the new value, so snack underscore object equals null, or snack object underscore t is equal to null, return false. If the object's kind is not an array, return false. So if how do I do that? If object's kind is not an array, so if kind is not an array, return false. Is not equal to array, return false. If the index is out of bounds, return false. Remember, the array field has a size field. So if the array field has a size field. The array field, snack object. Which one does it mean though? Snack object. So snack object data the underscore array is, so if the index is greater than that, I think it's that, set the value in the elements array specified index to the new value. Return true. Return true. Set the value in the elements array. So snack object dot data dot elements. Is it like that? The array. X equals value like that. Whoops. Okay, so if the object is null, return null. So if snack underscore object is equal to null, then return null. If the object's kind is not an array, return null. So if snack underscore object kind is not equal to array, then return null. If the index is out of bounds, return null. So if index, and then return the value of the elements in the array at specified index. So Oh yeah. Uh-oh. Should not access outside the array. Greater than or equal to. There we go. Okay, length. Last two. So now that we have all sorts of SNEC objects, integers, floats, strings, arrays, we need a convenient way to get the length of any SNEC object. In Python, SNEC lang's dreaded competitor, it's as easy as print length blah. As a Python dev, you don't have to know the value of x ahead of time because Python keeps track of it under the hood for you. You want the same capability of SNEC lang. So in SNEC object C, complete the SNEC lang function. So if the input is null, return -1. So if object is equal to null, return -1, which we've chosen to indicate failure. If the input is an integer, its size is always 1. If the input is an integer, I guess, okay, if SNEC object T equal to integer, then return 1. If objects kind is equal to float, and return 1. If the input is a string, it's the size of the string in bytes. So if object kind is equal to a string, then return length of the string in bytes. So str length equals object data dot is it like dot v string or something like that? Data object data like that. V string like that. If the object dash kind is equal to vector 3, then return 3. Input is array. If I could have done a switch on this, I guess. Oh well, halfway down thing now. Array, then return input is the size of the stored. So it's going to be object data dot v underscore array dot size. If the input is none above return thingy, so return -1. Whoops. Do that. Right, pretty confident in this, so let's go for it. Oh yeah. Could have done it with a switch. Just realised, but never mind. If you're familiar with Python, you're familiar with how Python objects have an add method. It allows developers to specify custom logic for different types of objects. For example, adding two integers, we want to behave like this, but with an array, we probably want it to work like this. Assignment. This is the final lesson on objects, and it's a big one. Take your time. You'll be using a lot more functions, a lot of the functions you wrote in the past chapters to complete this one. Oh my god. Oh. Okay. Complete the snec add function. Accepts 2 pointers to snec object T, objects A and B, and returns a pointer to the new snec object to the result of the sum. So if either input is null, then return null. So if A is equal to null, or B is equal to null, return null. So if A is integer, oh gosh. Right, let's whip out the switch case. Switch. So I guess switch a kind, I guess case. So case A is an integer. Case like case integer syntax colon with a break. Okay. Oh, I definitely want to give up on this one, but we will not. If turn null. So I guess if b dash kind is equal to an integer, and then that one would be if b kind is equal to float. If b is an integer, return a new snec integer with the sum of the two integers. So return with the sum of the two integers, return a dash a data b int. So then if case float, if b is an integer, return. So we're floating the integer. Float returns, the float 2 floats, anything else returns and all. Can shorten this a fair whack. I think those can be just the same, right? Yeah, it doesn't really matter. If a is a string, so this one case string. If b is not a string, then invalid operator. So if b dash kind is not equal to string, then return no. Otherwise, calculate the length of the new string by combining the length of the two strings, properly handling null terminator. Oh god, no. Oh. Calculate the length of the new string by combining the length of the two strings, properly handling the null terminator. Oh. Calculate the length of the new string by combining the length of the two strings. So new so length equals, and it's going to be a dash data dot v underscore string dot size. Is that right? String length that plus so then allocate memory for a new temporary string called using calloc. So char temp underscore string equals calloc. And it's going to be it's going to be new underscore length. It's going to be size of string, was it? Like that. I think roughly like that. Use string cat to append the data from A and then B into the temporary string. String cat. Create a new string and pass in the create a new next string. Ugh. Oh no. No, not bin mode. String object. So free the memory for temp underscore string, and then return the new string object. Return. Why is the thing all out of whack? The indentation. String underscore object. I think this is pretty much right. God, this is a long one. Hope the next two things are not so in like thingy in. Case vector 3. If B is not, yeah, okay, so just off the bat, B kind is not a vector 3, then return null. Otherwise, create a new snack vector 3. Recursively call snack add. struct the create a new snack vector 3. Recursively call snack add for each of the x, y, and z fields, for example, vector which will result in recursively call snack add. I don't have to do that, so I'm just going to skip on that for now. These are parts I'm not sure about. So, case array. If b kind is not equal to array, turn null. Create a new snack array. Find divide arrays equals this. New snack array size iterate over each index array. We got anything for length? So it would be a data dot b array size it has to be size of like that. Then combined arrays. If A is not only above case, whoops, valid operation return null. Expected expression. Oh, default. Default. Not as many errors as I thought there would be, actually. A lot of semicolons missing, though. String 15. Calloc bits allocate size t size number of objects, size of each object. So incompatible integer to pointer conversion, returning int from a function result type. So data v int. What's wrong with that? Okay, can't shorten it. I'm gonna have to thingy it up, split it up. Just kind of annoying. So I can't do this any shorter. I gotta do it the long way. That's really annoying. It's probably a smarter way of doing it than what I'm doing. That's the problem. So on line 42, too many arguments the function call expected single argument. Whoops, I'm a dummy. I'm gonna have to call Boots in, otherwise I'm never gonna get through this tonight. How am I doing? Tell me, Boots. Your close club, let's focus on that failing float test. So, for your float case, what fields are you adding the two branches? Are you ever reading vfloat or are you accidentally using vint? Oh no, simple. Right, got that working. So, for string concatenation, Does colloc take count size or size count? Should you allocate length +1 and pass bytes, colloc and bytes, or colloc? For vector 3, instructions say to create a new vector whose x, y, z are the sums of the corresponding components. How can you reuse snakeadd to build each component? For an array, let's go to the array. Are you using sizes themselves or the number of elements when creating the combined array? After creating it, how you copy elements? Oh. Let's put how about now? Okay, so string. So string y allocate length +2 and colloc new length and 2. What's the right total bytes and parameter order for colloc to ensure exactly one null terminator? Whoops. Colloc. They're open still. Number of objects, size of each object. So I was right. Right? Number of objects and size of each object. Oh, I'm a dummy. Why am I... Is it like that? Is string right now? Getting there, but a few string-specific questions for you to ask you, encoder. Why are you adding +2 to combine the length? How many bytes do you actually need for the concatenation plus single terminator? Are your arguments in the right order? Count size. And are they the right value? Should you allocate characters by pairs of bytes? Let's just submit and see what we get. How badly we do. We almost get it. So, string cat. What must be true about the initial contents of the destination buffer? Oh no, not the thing again. If temp string is equal to null, then return null. After allocating the buffer, how can you ensure it starts as an empty C string? How's everything now? I ended up spending a whole night on just on this. Oh, okay. So array. Array. When creating a combined array using the number of elements or the byte size of the size fields. What should the length be in terms of size? Well, that's what I thought. Because it was a size of, wasn't it? So is that not... That's not right then. After allocating, how do you copy items? Which indices should you fill from A and which from B? How do you get set fit in? Look at the array one again. So, done that. Otherwise, combined arrays. Each index in A. Do the same for B. Uh, can you help me with the array loop? I have to do this myself. So for, I guess, I'm gonna do two for loops. So for, and Lord help me if I remember the for loop syntax. So for so for loop. So I guess for int I equals 0, I is less than that, then I plus plus. Okay, so get snack array, so it'll be v array elements. It'll be a data dot v underscore array dot elements I. Oh, it's only that, isn't it? And then I like that. Snack object is going to be I don't need to see that, do I? Oh, it's going to be a lot less hassle than that. A combined arrays, a um, um, swap, I guess, something like that. We'll do the same for B. Boots, how am I doing? Where are you writing these elements in the combined array? Should they start at 0 index or the index? Yep. What destination index should we be using when copying bi into combined arrays? In for the second loop, try setting instead of I. How about now? Looks good. However, vector 3, you're returning a new vector built from A's components unchanged guiding step. Right. Right, okay, yeah. So vector 3, I was just kind of clueless on this, my brain's running out. So for each component call sneck add to the corresponding components of A and B. Use those three results to construct the new vector. Sx, sy, y, z, z. Is this it? Is this all done? Oh no. Oh, semicolon, semicolon, semicolon. Oh, thank goodness. Oh my gosh. Getting through that, gee whiz. Right, okay. So now we're on to garbage collector. So let's see how we do with this because it's 9:30. Come on, I just want to try and get this done tonight. Garbage collector.
What is a garbage collector? In C, we've been manually managing our memory, which is not only difficult to do, but tricky to say. I always feel like I'm going to make a big mistake while I'm talking about it. However, that's not the only strategy for managing memory. There are alternatives like the Rust strategy, which uses a borrow checker, which, while still including sort of manually, truly the Rust compiler is the one that determines whether an object's lifetime is complete or not, and if so, it will free that object. However, a garbage collector is quite different. In garbage collection, the language itself, for example, Python or JavaScript or Go, determines if a particular object or value is still live. Live means that the value could possibly be useful. If we had a variable that was created inside of a function, and then the function returns without referencing that variable anymore, we want to give that data, that memory space, back to the operating system. In that case, we would consider that object no long borrow checker, which, while still including sort of manually managing the memory, truly the Rust compiler is the one that determines whether an object's lifetime is complete or not, and if so, it will free that object. However, a garbage collector is quite different. In garbage collection, the language itself, for example, Python or JavaScript or Go, determines if a particular object or value is still live. Live means that the value could possibly be useful. If we had a variable that was created inside of a function, and then the function returns without referencing that variable anymore, we want to give that data, that memory space, back to the operating system. In that case, we would consider that object no longer live, right? Because there's nothing that could possibly reference it. It's useless. And in garbage collected languages, it will figure that out automatically for you. However, it's not free. The garbage collector still has to use some algorithm to determine what values are still alive or not. And like many other languages, for example, in Python, a lot of Python is written in C, or at least one implementation of it is in CPython. That garbage collector may be written in a different language. So let's talk about some of the algorithms that are useful for garbage collectors to determine whether a particular value is still live. The first kind is called reference counting. Reference counting is probably the simplest version of garbage collection. And what it is that every object has an additional field that is its count. And when you create the object or some other variable references the object, consider something like a list. If I have a variable foo and I put it inside of a list, okay, well now the reference count for foo might be 2 because it's one for itself and then one for this list. Now when we remove that list, or maybe we pop that element out of the list, we're going to drop its reference count by 1. And maybe if we return from the function that created foo, now its reference count might drop to 0. Once an object's reference count drops to 0, then we give that memory back to the operating system. Naive reference counting has some downsides, like an inability to track cycles, and it is quite expensive because every time we do an operation, we have to go modify all of the objects that we're touching. Because of that, people thought of other strategies. The other primary one that we're going to cover is mark and sweep. Mark and sweep is an idea that we'll be able to find all of the variables that are directly referenced by our stack frames, generally speaking, and then we will trace through all of the connections of those variables to find any other ones that are referenced by the roots. Once we've done that, we'll be able to determine, aha, I see all of the set of variables that are directly referenced and indirectly referenced, so any of the variables that are not marked, we can sweep those away. Really, the sweep is actually the search, but I kind of like to imagine you sweeping them back to the operating system. Mark and sweep is a bit more complex, but it can handle certain cases that at least naive reference counting can't handle, like a list who references another list who references back to the original list. See, that's a cycle. That's a problem for reference counting. You'll never get down to 0, but for mark and sweep, if none of the roots touch either of those lists, we'll be safe to mark them as not alive and free them and give them back to the operating system. Additionally, mark and sweep doesn't require us to do operations every single time that we touch or reference a variable. We only have to do the work when we do something often referred to as a GC pause, a garbage collector pause, where the garbage collector is going to do some work to go check which variables are still alive. One of the key things that I'm trying to emphasize here is that garbage collection is not free. There will always be some work for the language runtime to determine, is this particular value still alive or not? In languages like C, the programmer has to do that ahead of time and hopefully remembers to do it correctly. Or in Rust, maybe the compiler does some checking for you to let you know that. But in garbage collecting languages, you pay that expense at runtime rather during development time. That's one of the trade-offs you have to decide when picking a language, is where do you want to pay that cost?
Makes sense. Okay, as you're painfully aware, we've manually managing memory throughout the course with our C code. However, SNEClang, the language we're building, has automatic memory management. Specifically makes use of a garbage collector. In C and C++, management of heap memory is done manually with malloc and free, and new and delete in C++. Rust has a compile time system that ensures memory safety. Because the compile time system ensures memory safety. Zig gives the program access to allocators to manage memory. These are all examples of manual memory management. The programmer has to write code that keeps track of and frees memory. A garbage collector is a program or part of a program that automatically frees memory that is no longer in use. Languages like Python, Java, JavaScript, OCaml, even Go use garbage collectors as the code is running to manage memory. It's automatic memory management. Automatic memory management can be a huge productivity boost for developers. Less code and sometimes fewer memory-related bugs, but it typically comes with a performance cost because, like Forrest Gump, the garbage collector is always running. It's no coincidence that C, C++, Rust, and Zig are all great choices if you need to squeeze every last drop of performance out of your code. Which language makes use of garbage collector automatic memory management? It's Go. Oh my god, right. How much code writing we're going to be doing? Oh gosh. Oh my god. Oh, maybe we're not finishing tonight, guys. Oh no. Let's see how we do. One of the simplest ways to implement a garbage collector is to use reference counting algorithm. It goes something like this. All objects keep track of a reference count integer. When that object is referenced, its reference count is incremented. When an object is garbage collected, the reference count of any object it references is decremented. When any object's reference count reaches 0, the object is garbage collected. So in snec object h, add a ref count field to snec object t. Ref count field. So I guess it's going to be an int, right? Ref count. In snec object C, complete the new underscore new snec object function, allocate a new hit and 0, initialize its memory. And I've immediately forgotten how memory allocation work. I suppose it's just 0, isn't it? Set the ref count to 1, so object ref count equals 1. Return the pointer to the new object, return object. I think that's it. Yay! Right, maybe we will get through this. So increment, we need to be able to increment the reference count of SNEC object at any time a new reference to it is created. Complete the ref count function. It should increment ref count on a SNEC object. If the object is null, it should do nothing but safely. So if object is equal to null, then return null. Should do nothing but safely. Return 1. It's not equal to null, then object ref count plus like that. All right. See how it does. See the solution, is it the same as ours? Return, oh, they always want to return from that. Okay. Right, that's fine. Decrement and free. So now things are going to get a touch more complicated. In a recounting garbage collector, the interesting stuff happens when the ref count equals 0. That's when the garbage gets collected. When the ref count reaches 0, there are no references to this object anymore. So we need to free the memory automatically. That's the whole point of a garbage collector. For our first pass at this, we will only handle integers, floats, and strings to keep things simple. As we go a little further, we'll implement it for the rest of the SNEC object types. So complete the ref count decrement. Function handle null objects gracefully. So if object equals null, then return what was the solution on that one again? Just return. Okay, right, return like that. Decrement the ref count. So object ref count minus. Then check if the ref count reaches 0. If call, count on the object. If object ref count is equal to 0, then ref count return. Okay, I think I've done that. Ref count free. If the object is an integer or a float, so if object kind equals integer or object kind equals float, free the object itself. We don't need to worry about the data inside the object because it's stored directly in the object. Free object. If they're going to type, do nothing for now. Return. If the object type is a string, object kind equal to a string. Whoops. Then free the inside object, then free the object itself. So free string and then free the object and then return. I'm pretty sure that's it for that. Not quite. Oh, semicolon. Go, we're getting through this one. Right. Okay, we've arrived at our first container type. What makes vector3 not like other types is that it holds other SNCC objects. That is, it references them. They are contained in its X, Y, and Z fields. When we create a vector and place objects in those fields, we need to increment the ref count of each of those objects. Otherwise, we might accidentally free its contents and be left with a vector holding garbage memory. So update the snake vectors 3 function. It should ref count inc each of the 3 objects. Update the ref count free function to handle vectors. It should ref count decrement each of the 3 objects to automatically free them if they hit 0. Snake vector 3 should ref count inc. Okay, ref count 3. Now vectors. It should ref count decrement each of the 3 objects. Object they see how it does. Huzzah! Wow, this is way faster and way easier than all the last stuff. Crikey. So arrays, ref counting for an array is similar to the vector 3 kind. However, an array has a dynamic size, which will add complexity. So update the SNCC array set. Increment the ref count of the object that is being set into the array. Increment the ref count. Increment the ref count of the object that is being set into the array. Value. If there was already an object stored in that index, decrement the ref count of that object. If there's already an object stored in that index, decrement the ref count of that object. Okay, so if the object is an array, if there was already an object stored at that index, decrement the ref count to that object. If the object is an array, update free count. Okay. Case array. Case array, if the object is an array, update the ref recount to iterate over each element from 0 to size. Free the array itself for the elements field. Oh, we're doing. So for, let's try and remember the syntax. So for I equals 0, and then object data dot v underscore v underscore array dot size, I think. I is, say that is greater than I, and then it'll be I plus plus free. So then free iterate over each element. So object v underscore array dot elements I, and then at the end we're just free the array itself, the elements field. Free object v underscore array dot elements. Oh, there's quite a lot wrong with that. Hold on. Whoops. Hint. Free. Oh yeah, whoops. Data dot, like that. Data dot. Hey, got it. Got it. Last one on this one. Maybe we could get this done tonight. Okay, ref counting review. One of the great things about how we implemented our ref counting garbage collection is that the garbage collection logic was all nicely encapsulated in the new object functions, and the increment, decrement, ref count functions that occur automatically within the container types. In other words, the SNEC add function that we wrote in the last chapter will automatically handle the ref counting for us. There's no need for us to allow any of the garbage collection logic to leak out into the rest of the code base. Yay! It's pretty cool how a garbage collector can be implemented in a simple way that stays within the confines of the objects themselves. Why doesn't SNEC add function need to take care of garbage collecting the resulting object? Because we coded the garbage collector logic to happen automatically whenever reference count hits 0, because the SNEC add function doesn't work with our object types, because ccompiler does garbage collect. That one. How's that? Oh my goodness. Right, we've got 10 lessons. Can we manage this? I have no idea. Let's have a crack at it and see if we can manage. Let us have a crack indeed. Okay, we built a simple reference counting garbage collector. It can handle simple types like int and float, dynamically allocated types like string, static container types like vector3, dynamic container types like array. However, there's one little problem with our implementation. Take a look at this code. SNEC object first, SNEC array 1, SNEC object second, SNEC array ref counts first 1 and second is 1. SNEC array set first, second. Ref counts first is 1 and second is 2. Then decrement first is 0, second is 1. Ref count decrement second, ref counts first is 0. Blech. We create a first array and shove the second array inside it. Everything here works as expected. The trouble arises when we introduce a cycle. For example, first contains second, but second also contains first. So, assignment. Run the code in its current state. Notice that the assertions fail, even though we decremented both the first and the second arrays ref counts. Neither were freed. Ref count equals 0. Fix the assertions to pass by updating them to match the sad reality of our current implementation. Fix the assertions to pass by updating them. Observe. The reason both ref counts are stuck at 1 after being decremented is because first has its ref count decremented. It already had 2, so it only drops by 1, which does not trigger a free of the second array. This doesn't happen when ref count is 1. Because second still has 2 ref counts, it also only drops to 1, which fails to trigger a free of the first array. In other words, we have a cycle and a simple reference counting garbage collector can't handle it. Fix the assertions. Fix the assertions to pass by updating them to match the sad reality of our current implementation. Okay, so first has 1 and 1. Then SNEC array first, 0 second. So first is 1, second has 2 references. Then we put first and second, it's 2, 2. Blah, blah, blah. Okay. Pros and cons. So to solve our cyclic reference issue and to force you to implement another garbage collection algorithm, We're going to implement a mark and sweep garbage collector. So pros of mark and sweep can detect cycles and thus prevent memory leaks in certain cases. Less on-demand bookkeeping. Remember, all the work done in the garbage collection is wasted. It doesn't make your GPT-4 wrapper custom AI product run any faster. Reduces potential performance degradation in highly multi-threaded programs. Ref counting requires atomic updates for thread safety. Cons of mark and sweep. More complex implement. You'll see. Oh god. Oh god. Can cause stop the world pauses when lots of objects exist and must be freed, resulting in performance. Higher memory overhead. Less predictable performance. Assignment. We'll be using a VM underscore T struct that stands for virtual machine type. This VM underscore T simulates what would normally be tracked if SNEClang were a fully functional interpreted language. It's not. This virtual machine is much simpler than a real one because all we care about is demonstrating the garbage collection aspects. You can spam lane if you want. Write your own programming language course from Boot.dev. Please don't. I have wife and kids. Open vm.h and take a look at VM. Take a look at the VM underscore T struct. The frames field holds a stack of frames. Stack T. Stack of frames which are pushed and popped as we enter and exit new scopes. For example, message 1, this is in scope 1. This is in scope 2, this is in scope 3, with everything. At each of the scope entrances, in this case function calls, a new stack frame is pushed onto the frame stack. When we exit a scope, a function returns, we pop the stack frame off the frame's stack because we use a void asterisk. To work with generics in C, you can't actually tell what the data type held by stack T is for each field. We'll write some wrapper functions later to help us make sure we don't actually accidentally push the wrong kinds of data into our stacks. Yay, C! The objects field is also a stack but holds SNEC object T pointers. So in VMC, complete the new VM function. It should allocate space for thingy on the heap. I get tired of writing this, so I'm trying to find something to just copy and paste. I don't think there will be. Ah, crap. Right. Muscle memory, here we come. Right. Allocate space for VMT struct on the heap. So VM, let's go T. Struct. I can't do that. Okay. Let's call it temp for now. Because alloc. So allocate space for VMT struct on the heap. So I guess it'd be size of VM underscore T. Init on if temp is equal to null. Initialize the frame stack with a capacity. Initialize the frame stack with a capacity of 8 and the object stack with a capacity of, look at the VMT thing again. VMT frames. temp dot what was it? Frames. Using the stack new function. Where's that? And the objects of 8. Return the points in the new VM thing, so return complete the VM free. It should free the frames and object stats. Remember, we wrote a special stack free function for this. Free the VMT struct itself. Where was the stack free function? Objects and then the thing itself. That was easy enough. Stack frames. So think back to the warnings I gave you about working with void asterisks data types. It's easy to push the wrong kinds of data onto a stack T because, like Starbucks, Wi-Fi, it will let anything in. So to prevent us from shooting ourselves in the foot, we will create some functions that are more type safe and make it much more difficult to do the wrong thing when interacting with our VM underscore T wrong things like ccompiler won't stop us doing this. But we want to make it easier on ourselves to only push frame T asterisk types into frames. So we'll write some wrapper functions to help us. So complete the frame push function in VM.c should stack push a frame lagably. Stack push. C stack underscore push. Whoops. Hold on. Stack push. Where's that function? VMH. Complete the VM new frame. Allocate a new frame onto the heap. So, frame underscore t. New underscore frame equals malloc size of guess frame underscore t. Initialize the frames references with a stack new or new underscore frame equals null. Whoops. Then return null. Initialize the frames references with a stack new capacity. Initialize the frames references with a stack new capacity. All right, okay, right. New underscore frame dash initialize the frames. Push a new allocated frame onto the VM frame stack. Equals stack underscore new 8. And then VM frames equals new underscore frame. Return the new allocated frame. Turn a new underscore frame. I think that's all right. Complete the frame free function in that thing. So free frame t's references stack. We have a special function for this. PM free. I think that's it. Remember access with a null pointer of VM type aka virtual machine. Nope. What's wrong with this? I want to speed up tonight. I want to try and get a chance of finishing this. Okay. So in VM new frame, after you mark a frame T, why do you assign new frame to what type? Just stack new return, and what field on frame T should hold that stack instead? Oh, whoops. Is VM free? When freeing the frame in free frame, I get that. Oh, stack free. Right, okay. I had to look around for that. All right. There we go. Just a little poking in the right direction. So, tracking objects. So, our virtual machine needs to track every snack object that gets created. We are no longer going to track how many times an object is referenced, but instead check at garbage collection time if each object is still referenced at all. If it is, keep it. If not, free it. Assignment. So in VM .c, complete the vim track object, which adds an object to our VM-object stack in a more type-safe way. So VM-objects. We're going to use the stack push, right? So in Object-C, update the new snack object function before returning the new like object should ensure it's tracked by the VM. VM and then object. Okay. So, free. Recall the ref count free function that you wrote in the previous chapter. It should look something like this. Assignment. Let's rewrite the free logic for our mark and sweep, because the virtual machine is what is the one tracking objects. All of the ref count decrementing work can be removed. There's some very cool tricks coming up for mark and sweep to manage this, but for now you can just trust me that we'll correctly free any of the contained elements if they are no longer alive. So in snackObject.c, complete the snack object free function. Integer floating strings should all work the same as the ref count version. Non-container types. Complete the objects should all work the same as the ref count version. Non-container types. Text free doesn't need to do anything before freeing the object because the mark and sweep. So I guess VM3. Kind of lost on these instructions for the first part. Should free elements array but not the objects themselves, because mark and sweep will handle that. I think this is right. I have no idea on this one, to be honest. So VM3. So complete the VM3 function. Iterate over all the VM's frames and free them using frame free. So for I equals, whoops, int I equals 0. While VM dash, I forget to think of it. VM frames is stack count. Frames dot count, is it? So it goes to frames and then count. Count is greater than I, then I plus plus. And then reframe. And then we give it the frame. Okay, free the frame stack itself using stack free. So stack underscore free VM frames. Iterate over the objects and free them using the snack free object. Free the VM structure itself. Free VM. Oh, okay. Whoopsie daisy. VM frames to stack. What's the complaint about here? Passing stack T, aka struct parameter incompatible with neck object T. All the objects. VM objects. Stack free. What's wrong with that? Iterate over the VM's frames. The frames stack itself using stack free. Yeah, so frame free, yeah? Need speed up. What's wrong with my code? It's going to be a really dummy thing. My brain's just getting solution now. Yeah, okay, so question to guide you when you, what type is frames? Is it a stack or is it an array of frames? Do you access the ith is stored in that stack? Does the, I suppose the data? Oh, go back to that. Frames or is it a stack? Or is it a stack or an array of frames? How do you access the ith and stored in that stack? Does given that, should we call it free frame, pass it nth frame? Oh yeah, it's a reference, isn't it? It's a pointer anyway. Yay! Frame references. So consider this example of SNEClang scopes and stack frames. Yeah, in scope 2, we would add message to its referenced objects. Once again, this is a bit simplified from what you would do in a real production grade language, but the idea is the same. Each stack frame needs to know about all the objects they reference in an assignment. Complete the frame reference object function, so you should push the object onto the stack of references of the current frame. It should push the object onto the stack of references for the current frame. It. Nope. Completely. It should push the object onto the stack of references for the current frame. There we go. Okay. Mark and sweep. We finally have enough machinery in place to start thinking about the mark and sweep part of our garbage collector. So mark and sweep garbage collection was the first described by John McCarthy in 1960, primarily for managing memory in Lisp. It's a two-phase algorithm. Mark phase traverses the object graph, marking all reachable objects. Sweep phase, scan memory, collecting all unmarked objects which are considered garbage. Note, we don't have to keep track of how many times a particular object is referenced, like we did with reference counting. Instead, we can keep track of which objects are referenced in each stack frame. And then traverse our container objects, looking for any other referenced objects. That's what traverse the object graph means. A fancy way of saying look for objects. So in snack object H, add a is marked boolean to our snack object T. Is underscore marked. Is it boolean or is it bool? In should ensure that is marked field is set to false when we create a new snack object. So object dash is underscore marked equals false. Yeah, so it's not boolean, it's bool. Huzzah! Oh, 3 left. Come on, 3 left. So Mark, to do, would it be funny to just have a video clip of me going, Mark? And that's it. I'd advise against it. In some mark and sweep implementations, you'll see different ways to mark root objects, the objects directly referenced by stack frames. However, in our simplistic VM, it's a bit easy to find and mark all of the directly referenced objects. You'll see why when you write it in a moment. Assignment: complete the mark function in vm.c. It should set every object that's directly referenced by a stack frame to is marked true. So iterate over each frame in the VM, iterate over each references, iterate over each frame in the VM, iterate over each references object in each frame. That object, okay. So for int I equals 0, and then so I forget the VM thing. VM frame. So VM dash frames, and then stack T count. Dot count is greater than I, then I plus plus. And then for int j equals 0, and this is going to be Through each references in each object in each frame. The come on. Iterate over each references object in each frame. So I guess it's going to be frame underscore t current underscore frame equals the frames data I, and then it's going to be J plus plus. So then we're going to be frame references J dot is marked equals true. Is that going to work? So close. First up, you get the references, get that one. Data frames. References. I need your boots. Hi, close. Come on, boots. Help me finish this off tonight. What is the type of... Yeah. What is the type? After you retrieve it as a frame T, how do you access a reference object inside that frame? What is the type of frame references look at in stack H? How many items are stored in stack T? How many items are stored in stack T? Once you reference an item from frame references, what is its actual type? Which field on that type needs to mark it? In your inner loop, are you indexing the stack correctly? Are you indexing between references as an array of struct rather than a stack T with a data array? Try to use the count of each stack T for loop bounds. Pull from data array of each stack T. Cast each item. I'm lost. I need more help. Ugh. What is the type of VDM frames? It's a stack T. Its items live in VM frames. Data are stored in void 2. What should each item be cast to? After frame, what is the type of current references? Is it also a stack? Where do the referenced objects live? What should each of those be cast to before use? Once you have snack underscore object underscore T object equals that. And then object like that. Oh God. Concretely inside the loop you want to use get frame data I, that's right. Get snack object current frame. References data J. And it says marked as true. Ugh. God, what a pain. Trace. Oh my goodness. Oh, this is one of the larger assignments. Take your time, you're almost done with the course. Oh, goodness.
Marking, we can start doing the tracing section of Mark and Sweep. This is important because we have scenarios like the following. Consider the function getList. It creates a variable a, stores the value as 5, and it's going to return a list with a inside of it. We then could call this function and store its result in L for list. Now, what we need to consider here is when are we going to free any of these values? When we're doing this, we should start by thinking about what are the globals we have, and then what are any stack frames that we're going to create as we execute this program. The first thing that will happen is we'll create a new stack frame when we execute getList. This will create room for any of the variables that we have, like a, and store its value as 5. And then we're going to create a list that holds a, and we're going to return this. Before we exit this stack frame, the garbage collection is quite easy and already handled by simply marking all of the things directly touched by either globals or stack frames. So this part's quite easy. Everything here is referenced, so everything would have is marked set to true, and then would not be collected when we get to our garbage collection phase. However, things are going to get a little bit tricky after this stack frame is popped. Once we return this list and then pop off the stack frame, we're going to have effectively a global L, and it has a list with the value 5 inside of it. But what you should really be thinking is that this is a list with the variable a, which currently has a value of 5. Now, what we need to decide here is, and this is where the tracing part comes in, is a still alive? This is tricky because intuitively we sort of know, yes, we're still using that value that we allocated for a, but how are we going to sort of prove that in our algorithm? So what we're going to do here is we first do our mark phase. Mark is going to traverse all of our global variables, which it will see L. Once we get to trace, what you're about to implement, that's where we're going to say, aha, I see that I have an array. I will iterate over all of the elements in the array, and then I will mark that value. And that's when we encounter a, and thus we can do a is marked is true. This is the fundamental thing that we're going to be doing as we're tracing. We're going to be working with container types like lists or vectors, and we're going to be able to check and make sure, sort of traverse this graph to make sure that every single item that is referenced by a global or stack framed value is marked so that we don't sweep those away. This will ensure that all of the live values are still marked and will not be freed during a garbage collection cycle.
Well, that was a lot to take in. Hey, TechCast. Is it not a bit easy for me? No, not in the slightest. This is not easy for me because I had not done C before. I don't do languages of memory management. So this has been an absolute ball ache. It's been really stretching the boundaries. Right, let's have a look how much. Okay. Right. Trace is the tricky one. Okay, so now let's just try and nail this, okay? So now that we've done the first and simplest part, marking, we can trace through all of our objects and determine which ones connected to the roots. For example, define get list a equals 5, return a, print get list. If we run this code, it will return a list with an integer a inside of it. Our current mark function will mark the list, but won't mark the integer a, which means that when we go to sweep the memory, we will mark the list, but not the integer a. We then free a while it's still being used, and the operating system could then fill that memory with something else, which would be very bad. So we need to prevent this. But we also have another problem. This blah, blah, blah. In the above very dumb example, we create a list that references itself, and then return a completely unrelated list. In our trace, if our trace function looks for any object that is referenced by any other object, it will consider a alive because it has a reference, albeit to itself in this case. In fact, A is unreachable. A is unreachable because when getList returns A, it's no longer used anywhere. Tracing solves these problems. To be clear, tracing is part of the mark phase of mark and sweep. It's where we mark all the objects referenced by our root objects. So assignment. This is one of the larger assignments. Take your time. You're almost done with this course. Oh. I'm determined tonight is the night that we get it done. Okay. Complete trace mark object. So if the object is null or already marked, return immediately without doing anything. So if object null, just return, or object can't keep it all in my head. Snack object is marked. True. Otherwise, mark the object and push it onto the grey object stack. Object is marked equals true. And then push objects on the grey stack. So we have a stack push. Grey. So objects, object. So I think that's right. Complete the trace blacken object function. You can see, so if the object is an integer, float, or a string, do nothing. These don't contain references to the object. So if object, I suppose we do switch, can't we? So switch object kind, and then I guess case integer, case float, case string, whoops, string return. If it's a vector 3, call trace mark object as refield. So case vector 3. Object guess case array. Each element. So I guess for object, wait. So int I equals 0, and then object, and what was it? I'm losing track of things. So object object v array Oh, well, that's size greater than I, and then I plus plus. So that'll be object v underscore array elements I. Array underscore objects trace mark object. I think that's done complete. Trace, create a new stack, capacity 8. Okay, so create a new stack with a capacity of 8. Stack underscore t. Called gray objects. Gray underscore objects equals 8, and then if gray underscore objects is equal to null, then return. Iterate over each of the objects in the VM. If the object is marked, push it onto the gray object stack. VM T objects. Objects. T objects is stack T. Count. If the object is marked. So if VM dash objects stack T data underscore objects. While the grey object stack is not empty, pop an object in the an object of the grey property set callback and trace on the object. Stack pop underscore item. Let's see, is this the one? Oh no. Let's start with here. So line 11. stack underscore t is so current underscore object equals that. So current object whoops, semicolon. This is stack h. Objects. So stack h. Objects. Array of objects. Check data. Snack object. Data vector 3. Oh, I'm almost there, Boots. Come on, Boots. Objects. VM. Objects. Stack T. Data. What am I missing, Boots? Oh, I'm so close. Hold on. So power, let's poke around two main issues in trace. The actual type, so blah. If it's snack object should current target be void tree or snack object T. Whoops. How would that change current object access so snack object? Is marked. Whoops. Oh, is this fix everything? Is this the one? Oh no. Which part's not true? Oh no. So close. So close. Your second loop. What happens to the grey pop? If it shrinks, can this for loop stop early before stack is empty, leaving children process like lane? What loop condition would you consider trial? Okay. Popping should you? Yeah, it should be that. I don't know why I can't get my head around like the keeping things going like that. Must be it. Oh my god. We are on to the final bit. Come on, this is the home stretch. Right? Sweep is easy. Trace was probably the hardest part of the garbage collector. Every object now has an is marked field that we can use to determine if an object is reachable or not. All we need to do is iterate over all the objects in the VM and free any object that is not marked. Once it's freed, we can also remove it from our VM. One more thing that's not obvious about sweep: any object that is marked, we don't want to free right now, needs to be reset to is marked equals false. That way, the next time the mark phase runs, if it's not marked again, it will be freed in the next cycle. So assignment: complete the sweep function. Iterate over all the VM's objects. Okay. I am going to touch below this line because I'm going to steal this code. Sweep. So VM's objects. And it's going to be a snack object. Okay. If the object is marked, so if object dot is marked equals true. What? Then object is marked equal to false. Else, free the object and set the data at that position in the stack to be null. Okay. Free object. Set the data at that position in the stack to be null. Complete the VM garbage collect function. That's it. This is the function that runs the GC called mark, trace, and sweep. So mark, VM, trace, VM, and sweep. VM. Is this it? Hope you like the course. Great work. Hint. Oh, snake object free. Is this it? Is this the end? Oh. Huzzah. Finished. Complete. Oh my goodness. We are done, chat. Done. My goodness. This has definitely been the hardest course so far. You've finished everything. Might as well complete this course. Leave it Ross is like, this is an incredibly valuable course, although very difficult in some places. I probably won't use much of this again, but it's good to understand, learn, and try things at least once. It was a great challenge. Five out of five, can't fault it. I'll skip a review on this one this time because it's a lot of things. So, yes, rewards. Give me all the things. Oh, I got roll sage, level 70. Nice. Oh, does that mean go back to the dashboard? Yes, it's done. It's done. We're on to why? Feels like we should have more on this, but like, but now we'll be on to course 12 next week, and what is it, September now? We're going to start powering through these because like, that was 100 lessons, and it took us a while to get through, so we're going to have to go a little bit more speedy in the next one to try and get it done within a year. Well, I'll say the end of the year. Thingy, we just got to keep it up, we got to keep going. But yes, huzzah. So I'll share on X as well. I'll download it as well. As it wasn't. All right, let's get on LinkedIn and then let's be having it. So add to LinkedIn. Does he have LinkedIn? I doubt he does. There we go. That'll do. So that'll do. Huzzah. That'll do, peeps. So that means next week we're going to be starting the personal project, and it's got 4 things in it and stuff, so it shouldn't take too long. before we be moving on to Go. Which I'm looking forward to. There's a lot less. There's a lot less steps in. Well, there's a lot in the first one, but after that, there's some courses that have a lot less in them and stuff. And we should be able to get through them a lot faster than some of the ones that we've been through recently. So that is going to do it for tonight. So I'd like to say thank you all for watching. You were here. You witnessed. You were part of history getting this one done. So have a good night. Thanks for watching. Thanks for putting up with all the slowness and just the getting through. This has been a real slog and stuff. Have a good night, and we'll see you next week.